Welcome to the video. Today we're going to take a look at how to do a between participants MANOVA. So specifically we're going to look at a one-way between participants MANOVA, which just means that we have one independent variable. So the MANOVA is a bit like the ANOVA, so we're going to have an independent variable with separate groups. But unlike the ANOVA, which just has one dependent variable, the MANOVA has multiple dependent variables. So we're going to take a look at how to do this test. We'll take a look at the assumptions that this test has and how to check them, and we'll take a look at how to report the results of this test. So this will probably be quite a long video because there's quite a few assumptions to check. So if you're just interested in running the test itself or reporting the results, feel free to use the timestamps below to skip forward to whatever bit is interesting to you. So today we're going to imagine, if we take a look at this spreadsheet, that we have two groups. So we have an independent variable with two groups or two levels, and we're going to look at how these two groups performed on science tests and on maths tests. So we're going to imagine that participants in group 1 received like a theoretical class on science and maths, so they just did lots of theoretical work, whereas the people in group 2 had like a practical class, so they did lots of practical tasks related to science and to maths. And so the MANOVA is going to tell us, so we can think of science and maths, right, as aspects of academic performance. So the MANOVA is going to tell us whether there's a difference between these two groups with respect to academic performance by combining these two variables together. It will also tell us whether there are differences between these two groups with respect to the individual classes, so whether there's a difference between the two groups with respect to science scores and with respect to math scores. So these are the data, and if we go across to SPSS now, let's take a look at how to set up the file. So we can start off by going to variable view, and I will just enter, let me see, intervention. So this is going to refer to whether the participants received the practical class or the theoretical class. I'll just put science, let me see, score here. I'll put maths score here. We also want to actually have participant IDs as well, so I'm going to create a variable for this as well. So I should have done this first, but I can just insert a variable and then I'll just call this ID. Okay, so after that, I'm just going to specify what type of variables these are to SPSS. So intervention, that's our independent variable, and it's categorical, which is otherwise known as nominal. So I'm just going to select that from the measures row. And these two are continuous or scale variables, so I will select the scale icon for those. Another thing we need to do for intervention is use the values column to specify what the different levels of the independent variable are. So I'm going to use a 1 to stand for theoretical. So this is the theoretical condition. So those students received a theory-based class, and this is practical. So 2 stands for practical, and those students received a practical-based class. So I'll go to 2, practical, then add, then I'll go to OK, and then I'll go over to data view, and we can see that these variable names have appeared at the top of these columns. And so now it's just a matter of copying and pasting these data from this Excel spreadsheet. So copy that and paste it here. And we can see that those 1s and 2s have been replaced by the names that I just gave to those numbers. So theoretical is 1 and practical is 2. If you're still seeing numbers here, you can just check in the view menu that values labels is ticked. Alright, so if we take a look at some of the assumptions of the MANOVA, so I've written them down here, so we can see that sample size is something we need to check. We need to check normality, outliers, linearity, homogeneity of variance-covariance matrices, and multicollinearity. So there's quite a few things to check. So let's start with sample size. This is just a matter of, well, so the description here, as many cases in each cell as there are DVs. So what does that mean? So cases in the case of studies with human participants, you can replace cases with participants. So we take a look at some tables I've created. I'll show you what this means. So if we have an independent variable with two levels, which is to say we have two groups, and if we have two dependent variables, we have 4 cells, and we need to have 2 participants in each one of those cells because we have 2 dependent variables. If our experiment had 1 independent variable with 2 levels or 2 groups, and if we had 3 dependent variables, because we have 3 dependent variables, we need to have 3 participants in each cell. So we go from having to need 8 participants to needing 18 participants. So actually you can do the MANOVA with a very small number of participants, as you can see. Obviously it's better if you have more participants, but you can do it with a very small number. So basically that's how you check the number of participants you need to do the MANOVA. So this is the minimum number. Okay, so the next thing then is normality, and we need to do this for we need to check univariate normality, and we need to check multivariate normality. So to check univariate normality, we can use Shapiro-Wilk tests. So let's take a look at how to do that first. So I'm just going to go up to Analyze, then down to Descriptive Statistics, then across to Explore. Then I'm going to transfer both of my dependent variables to the dependent list, and I'll transfer the independent variable to the factor list. I've got both ticked down here. I'll then go to Options. No, sorry, I won't. I will go to Plots. And I'm going to untick stem and leaf, but I'm going to tick normality plots with tests, and then I'll go to Continue and then to OK. Okay, so this is the output. So this output relates to the assumption of univariate normality, and we can really ignore most of it. The most interesting thing is this column here, so the SIG column in the Shapiro-Wilk section of the tests of normality table. So if we look at the science scores, in both the theoretical and practical groups, we have non-significant p-values. They're non-significant because they're above 0.05, and we see the same thing for math scores. In both the theoretical and practical groups, we have SIG values above 0.05, indicating non-significant results, and that's exactly what we want to see with this test. So that just indicates that the data were normally distributed in all of those different groups and for both of the dependent variables. So the process for checking univariate normality also allows us to check the assumption of univariate outliers, or the assumption that there aren't univariate outliers. So if we just scroll down from this test of normality table, I'm just going to scroll past these tables or these figures until I get down to these box plots. So this box plot here refers to science scores, and basically what we want to see is something like this, because it doesn't have something like this. So this 8 and 2 here refers to a row within the data set, and it's saying that the number in that row is an outlier. So cases 8 and 2 have particularly high science scores, and these particularly high science scores represent outliers. So that's not what we want to see, basically. And if we take a look at the data file, so here's number 2, and we're looking at science scores. So this person has 7, which you can see is higher than most other people, except person number 8, who has 7 as well, and that corresponds to what we see here. So 8 and 2, these two participants have particularly high scores. So those two represent outliers. We don't see the same thing here, so there are no outliers within the practical group compared to the theoretical group with respect to science scores. Then if we keep going down, we can see the same thing for math scores. So we've got the theoretical group, we've got the practical group, and again we don't have any outliers highlighted by SPSS in this case. So that the MANOVA does have some robustness to outliers, especially when they're mild. So if you see the circle here, that indicates that it's a mild outlier. If you see an asterisk there, it indicates that it's an extreme outlier. So if you had lots of extreme outliers or lots of mild outliers, we only have two, you might consider removing those cases from the data set. You might also consider performing a data transformation to address these outliers, to get rid of them basically. In this case, because we only have two mild outliers, I'm just going to ignore them. And what I could do in a report is just mention that there were a couple of outliers, and therefore the results should be interpreted with more caution. Okay, so we've now checked the assumption of univariate normality and the assumption of no univariate outliers. So we can now go on to checking the assumptions of multivariate normality and multivariate outliers. And to do that, we're going to go to Analyze, then down to Regression. I'm then going to go over to Linear, and I'm going to transfer this ID variable into the dependent box and the DVs into the independence box. Then I'll go to Save. I'm just going to tick this one here, so the Mahalanobis distance option. I'll then go to Continue, and then I'll go to OK. And what we're interested in this output is the maximum Mahal distance value. So in this case, we can see that the maximum Mahal distance value is 5.912. And that doesn't really mean anything by itself, does it? So we have to compare that to a chi-square table. And that chi-square table, used in conjunction with this maximum number, is going to tell us whether we have any problems with multivariate normality and multivariate outliers. So I have the table here somewhere. Okay, so this critical values table. Okay, so what we're gonna use this table to find out the critical values. The critical value, if we have two dependent variables, is 13.82. So we want our maximum Mahal distance value to be below 13.82, and since ours is 5.912, that indicates that we don't have a problem with multivariate normality or with multivariate outliers. And if you had, three dependent variables, you'd look at this number instead. If you had four, you'd look at this number instead. And if you found that your maximum value was above the critical value, what you can do, so the process that we just performed generates this variable here, and this gives you all of the Mahal distance values. And so if you knew that your maximum value was above the critical value, you could look through these numbers here, find any values that are above that critical value, and then consider removing that case or that participant from the data set. Okay, so we've now checked the assumption of univariate and multivariate normality. We've checked the assumption of univariate and multivariate outliers. Something else we want to check is whether the dependent variables are linearly related to each other. And the easiest way to do that is to create scatter plots. So we want the dependent variables to be linearly related to each other in both or all groups. So in the case of this example, we want there to be a linear relationship between the DVs in the theoretical group and in the practical group. So to do this, I'm actually going to use the split file function. And so the split file function will allow you to perform analyses on individual levels of your independent variable. So normally SPSS will analyze all the data from your data set at one time. But if you use this organize output by groups function, it will perform analyses and provide outputs that are specific to individual levels within your IV. So I've selected organize output by groups, and I've transferred intervention over to this group. So that's my IV. So then I'll click on OK. And then I'll go to Graphs Charts Builder. And I've actually already set this up. Okay, I'll just click Reset. So I'm going to click on Scatter/Dot. Then I'll double click this top left one. And then I'm going to transfer one dv to this axis and the other dv to this axis. It doesn't matter which way around it is. And then I'll go to OK. And now we can see that because we use the split file function, the output has generated two different graphs because we're looking at the each level of the independent variable. So this is the theoretical group, and this is the practical group. So we take a look at the theoretical graph first. We can see that there's kind of we can see some dots down here. So we can kind of imagine that there would be that these dots could be represented by a straight line quite effectively. And if we just double click on that graph and then go up to this bit here where it says add fits line at total, let me click on that. That's going to put a line through the dots. And we can see that that line sort of quite well represents those dots. So that suggests that there is an approximately linear relationship between those two dependent variables within the theoretical group. And if we just do the same thing with this one down here, so I've just double clicked on that, I'll go to this again, add fit line at total, just close this, and that comes up with this line, and we can see that this line does a pretty good job at representing the dots, suggesting that the two dependent variables are approximately linearly related within the practical group. So based on those two scatter plots, we could conclude that we have met the assumption of linearity. Okay, I'm actually going to check multicollinearity before this one. So we've checked these top four. Now I'm going to check this last one before checking this one. Okay, to do that I just need to remember to turn off the split file. So we're going to go to Analyze All Cases, Do Not Create Groups. Okay, so now SPSS is just going to start looking at the entire data set again. And so multicollinearity refers to when you have too strong of a relationship between your dependent variables in this case. So we want the dependent variables, if you're familiar with the Pearson correlation numbers, so we have an R value when we do a Pearson correlation, and that value is always going to range between -1 and +1, and the closer or the further away those numbers are from 0, the stronger the relationship. So if we have something like -8 would indicate a strong negative relationship, so as one variable goes up, the other one goes down. And something like +0.8 would indicate a strong positive relationship between those two variables, so as one variable goes up, the other variable goes up. And what we want to see in the case of the MANOVA is that there is a moderate correlation between the two dependent variables. So we don't want it to be too weak and we don't want it to be too strong. So ideally we want it to be probably somewhere between about 0.3 and 0.8. So we're going to take a look at how we can check that. So to do this, we're just going to go to Analyze, then down to Correlate, then across to Bivariate. Then we'll transfer math score and science score to the variables box. We've got Pearson's checked here, and I'll just go to OK. And we can see that this R value is 0.732. So we could describe it as moderate. There are different criteria for how to describe correlation values, but this is quite strong, but it's not very strong. It's not above 0.8 or it's not above 0.9. So it's quite strong. You could call it moderate, and I would argue that this value, because it's between 0.3 and 0.8, doesn't suggest that there is a problem with multicollinearity, so we can conclude that that assumption has been met. Okay, so we've checked most of those assumptions now, and the last assumption that we're going to check, so homogeneity or variance-covariance matrices, we're actually going to check this one as we run the MANOVA. So to run the MANOVA, we go to Analyze, then we go down to General linear model, then across to multivariate. So the multi refers to the fact that we have multiple dependent variables. So we'll tick on that. And we'll transfer the IV, so in this case it's intervention. We'll put that in the fixed factors box, and we'll put science score and math score, so these are both the dependent variables, into the dependent variables box. I'm also going to check, let me see, options, descriptive statistics, estimates of effect size, and homogeneity tests. Then I'll go to continue, and I think that's all I need, so I'm just going to go to OK. Okay, so this box's test of equality of covariance matrices is the one we're interested in when we're checking this assumption of homogeneity of variance-covariance matrices. And all we want to see is that the sig value is above 0.05, indicating a non-significant effect, and our value is clearly above 0.05, so that indicates that that assumption has been met. So we've now checked the assumptions, and we can go on to looking at the actual results of the MANOVA. So the first thing I'm going to look at is this multivariate test table. So just to recap, the MANOVA creates a variable out of all of your dependent variables, and it performs an analysis on that composite variable to assess whether there are differences between groups with respect to that composite variable. So in the case of this example, we can imagine that that composite variable represents something like academic performance, because it's made up of two variables, science and math performance, that are sort of subsets of academic performance. So we can see that there are several rows within each section of this table. We're not really interested in this top half, so we can just ignore this intercept half of the table. And we can pay attention to the intervention half of the table. We can see that when you have just two dependent variables, everything from this part of the table, from the f over to the partial eta squared, is identical. So it doesn't really matter which bit of this you look at which row you look at. If you had more dependent variables, then these values might differ. However, the value in this column does differ between these different rows. And the most commonly referred to is the Wilks lambda. So that's the one I'm going to report today. I'll show you how to do that in a minute. If you had violated some assumptions, or if you had a particularly small sample size, p-allows trace might be a good option because it's a bit more robust to violations of the MANOVA. But in this example, we're going to look at the Wilks lambda. And it's hard to infer much just by looking at these values, with the exception of these two here. So the partial eta squared is an effect size measure. The closer to 1 it is, the stronger the effect. The closer to 0, the weaker the effect. So we have a 0.3, so maybe we could indicate that we have a sort of moderate effect size. It depends on the criteria that you're using. And we have a sig value of 0.046. And because this is below 0.05, which is the commonly or almost universally accepted alpha for determining whether something is significant, we can conclude that there was a significant effect of intervention type on academic performance when we're looking at both of those dependent variables combined. So once we've established that, we can go down to the tests of between subjects effects table, and that's going to tell us whether there were differences between the groups with respect to the independent dependent variables. Okay, so we can look just at the intervention section. So this is just going to have the name of your IV here, and we've got science score here. And again, the most interesting thing is the sig value. One thing to consider when you're looking at these sig values is you might want to perform a Bonferroni correction. Because we have multiple tests here, the probability that we're seeing something just by chance increases. So sometimes researchers will argue that in that case you should divide your alpha, which is normally 0.05, by the number of tests that you're performing. So to be more robust, we might consider doing that. So if we have two dependent variables, we have two tests, we could divide our alpha by 0.05 to get 0.025, and we're going to use that value instead as the cutoff point for determining whether something is significant or not. So if we look at the intervention section, then science score, and we can see that this value here is below 0.025. We can conclude that there was a significant effect of intervention type on science scores. Conversely, if we look at the p-value for math scores, we can see that this value is above 0.025. So in this case, because we have applied the Bonferroni correction, we could conclude that there is not a significant effect of intervention on math score or math performance. If you weren't applying that correction, obviously because this number is below 0.05, you would conclude that there was a significant effect of intervention type on math score. Okay, so those are all the results. So let's take a look at how to report those. So I've divided this up into lots of separate sort of sentences because I think it's just easy to see, but probably in reality I would just report this all in one paragraph. So as usual, I just start by saying what test we did and why we did it. So a one-way MANOVA was conducted to examine differences in academic performance between two interventions, theoretical and practical. There were two dependent variables, science performance and maths performance. And then I'm going to indicate that we did several checks to assess these assumptions. So we've got normality, outliers, linearity, homogeneity of variance-covariance matrices, and multicollinearity. Okay, so we can start off by checking the normality, the univariate or normality assumption. So this refers to the Shapiro-Wilk tests, and I'm saying that these indicated that both dependent variables were normally distributed in both groups. And I've said P followed by S equals above 0.05. So that just means all of the p-values associated with those Shapiro-Wilk tests were above 0.05. And let's just take another look at where that comes from. So this is the first thing we did, and we just went down to this test of normality table and we looked at Shapiro-Wilk, and we saw that these sig values for both of the DVs and both of the groups, all of these values are above 0.05. And so that's why I've written all of the p's were above 0.05. And I've argued that this supports the assumption of univariate normality. So this next sentence refers to the assumption of multivariate normality and there being known multivariate outliers. And that just refers to this Mahalanobis distance value. So we saw, if we go back to that part of the outputs, okay, so this was this residual statistics, Mahal distance, our maximum one is 5,912, and we compared that to this critical value here. So we looked at the two dependent variables section of the table. We saw that this was 13.82, and 13.82 is obviously higher than that maximum value that we just looked at. So we can conclude that there aren't any issues with multivariate outliers or violations of the multivariate normality assumption. So the next bit refers to univariate outliers, and so I've argued that box plots indicated that there were only two mild univariate outliers. So what I'm implying here is that there wasn't really a problem with univariate outliers. And just to take another look at where that comes from, so we created these box plots. Right, so the first box plots, so the first two, so this one looks fine, no outliers. This one, there's two outliers, but they're only mild. And down here, we saw that these groups, the math scores, didn't have outliers. So as I mentioned before, I'm not going to do anything about this, but I might just mention it in the report somewhere in the results section, in the discussion perhaps, just to indicate that the reader should take some caution when interpreting the results, because there was a sort of minor violation of this assumption. And then I've just indicated that I would probably include these box plots as appendices. And this sentence here refers to the assumption that the dependent variables are linearly related, and I've argued that they were linearly related in both the theoretical and the practical groups. And just to take another quick look where that comes from. So that's from these scatter plots that we generated, and we created these lines of best fit, and we're arguing that basically the data can be quite well represented by these straight lines, suggesting linear relationships. And again, I've just referred the reader to an appendix where they could check for themselves whether they agree with that conclusion. So boxes tests, so this test relates to the assumption of homogeneity of variance-covariance matrices, and for that we just looked at where are you? At this boxes test of equality of covariance matrices table, and the only thing we looked at was this sig value, which is above 0.05, and so we've concluded that that indicates that there was not a problem with this assumption. Okay, so the final assumption is multicollinearity, and for that we ran a Pearson's correlation analysis, and this told us that there was a sort of moderate, perhaps quite strong but not very strong relationship between the dependent variables, and we've argued because it's not very strong, that means that we don't have an issue with multicollinearity. And so I reported the R value. I've just rounded that to 2 decimal places. I've reported the N number, so that's just the number of participants, and the P value I've reported as less than 0.001. So in APA style, when you see 0.000 here, it doesn't mean that the value is actually 0, it just means that, well, the number is just shown to the 3 decimal places, and actually there's another number down there somewhere, but we can't see it. So we just know that the number is less than 0.001, and so that's how we report that. Okay, so those are all the assumptions, and then we'll go on to actually looking at the MANOVA itself. So we're starting off by referring to the analysis that is performed on the composite variable, so the combined dependent variables put together. And we're going to say there was a significant main effect of intervention on academic performance. And if we take a look at where these numbers come from, so the first thing I've reported is F equals 3.72. So where does that come from? So that comes from this multivariate tests table, and I'm focusing on the Wilks lambda row. And then if we look at the F column, it says 3.72, and that corresponds with what I've written here. And these numbers here refer to degrees of freedom, so 2 and 17. Go back to the same table, and we've got 2 columns which both refer to degrees of freedom, df here and df here, 2 and 17. So that's where those numbers come from. The next number we have is a p-value, so sorry, wrong bit. P equals 0.046. So in APA style, p-values are reported as exactly as they appear, with the exception, as I mentioned before, when they're shown as 0.000 in SPSS, then you report them as less than 0.001. Otherwise, you use p equals and then just the exact value that appears in SPSS. So in this case, we've done p equals 0.046. And that just comes from the sig value here. And we've reported the Wilks lambda, so that's a lambda symbol, equals 0.70. And that has come from here. I've just rounded that to 2 decimal places. And then finally, I've got the partial eta squared. So this is the partial eta squared symbol, equals 0.31. And that comes from here. That's just been rounded to 2 decimal places. So that's how you would report the results of the analysis on the combined variable. And now we can move on to looking at the analyses that were performed on the dependent variables individually. So I've indicated that I used a Bonferroni adjusted alpha of 0.25. So I just divided the standard alpha of 0.05 by 2, and that gave me this adjusted, this should actually be like that, 0.25. And I've said that there was a significant effect of intervention on science performance, and this is very similar to the results we just looked at. But we're going to go down to the next table. So we've got the tests of between subjects effects table. I'm looking at the section of the table that contains my IV name. So in this case it's intervention. And I'm looking at the science score row within that section of the table. And the first value that I've reported is this F value here, so 7.46, which would be rounded to 7.47. And so we've got that here, 7.47. Then we've got these degrees of freedom, 1 and 18. So the 1 comes from here, so there's only one DF degrees of freedom column in this case. And so the 1 comes from this bit, so the intervention section of the table, the section of the table that contains your IV, and the 18 comes from this error section of the table. And next we've got the p-value, so p equals 0.014. That just comes from the SIG section, so intervention, science score, SIG, 0.014. And the last thing I've reported here is the partial letter squared. So that's 0.29. And that just comes from the last row. So I've just rounded that to 2 decimal places. And after doing that, so I've said that there was a significant effect of intervention on science performance. And because there was a significant effect, I've also reported descriptive statistics for that dependent variable for each group, so the theoretical group and the practical group. So I've said that scores were higher in the practical group compared to the theoretical group, and I've included means and standard deviations. So if we take a look at where those come from, so we're looking here at science scores in the practical group. So we ticked descriptive statistics when we were running this analysis, and so this has produced this table. So we've got science score, theoretical, practical. So we've got 4.7 and we've got 6.7. So that should correspond to these, yeah, just the other way around, so 4.7 and 6.7. And then we've got the standard deviations in the next column. So 1.42 rounded to 2 decimal places and 1.83 rounded to decimal places, 2 decimal places. And hopefully that's what we see here next to SD here and next to SD over here. And then these results are the equivalent of, they refer to the maths performance analysis, and the way you report them is exactly the same as the way you report the science performance results. So hopefully you can figure out how to write this based on the description of how to write this section of this paragraph. So that's about all there is to the MANOVA. Hopefully that's clear. If you have any questions about anything, just let me know in a comment and I'll get back to you. And thanks very much for watching.